Thanks a lot for the nice invitation. Yeah, so I will continue on the line of Andrea's talk. So my presentation will be to give, as the title say, an application, a geometric application of these definitions of timelike Ricci curvature lower bounds. And so the plan is to present an isoperimetric type inequality in this context. And so the plan of my presentation is to first give a very quickly overview on these TCD conditions, also because we have already seen very nice lectures on that, so we can be a little bit more faster on that. And then I will present first volume monotonicity result concerning the area of a Cauchy hypersurface in this context, and then an isoperimetric type inequality. So the result that I will present here are joint project together with Andrea, and it should be more or less appearing in a forthcoming paper, but there is no upper bound forthcoming, so just lower, just lower bound. Okay, so let's start with to recall the definition. And so it's the one that we have already seen. It's taking steps from the work on the smooth setting by Robert McCann and Andrea and Sur. And so we have a measured Lorentzian pre-length space. So you have this object with 6 entries. You have a space, a distance induced in the topology, a reference measure, a time-like relation, and a causal relation, and a time separation functions. And we have seen that this condition means that we have both the classical one and the weak version, depending on how many couples of probability measure you are asking this condition to be satisfied. So if you ask for every couple of probability measures that are time-like p-dualizable, we have seen the definition that means that the dual problem and that the dual formulation of the optimal transfer problem is valid, so the duality holds. So if for any couple of time-like p-dualizable probability measures, so this, as again, p is this exponent between 0 and 1, there exists a probability measure pi that it's moving mu naught to mu 1. Here I'm using the notation that Andrea has introduced in his previous talk. So we have a probability measure moving mu naught to mu 1, fully supported in the time-like relation, and we ask for the existence of an LP geodesic, along which the entropic formulation of the entropy, so here the entropy is just rho log rho with respect to the reference measure m, and rho is the density of the probability measure mu with respect to the ambient measure m. So you define this entropic formulations of the entropy functional. So you raise to the exponent, and you ask for this distributional inequality to holds along this geodesic. So if you want to write it in more without the derivatives appearing, so you can write it in as a type of distorted concavity property for the function un. So you just take the solutions of the differential inequality 1. So you just consider the equality case. So for instance, when k is strictly positive, they will be given by the solution by a ratio between sinus, where you have this t appearing here. And then what this condition is requiring is that the entropy along this geodesic to be concave, where the concavity property is weighted with respect to the solutions of the second order ODE. Okay, so this was the definition that we have already heard 2 talks about, so we can say that now. Just let me spend also one word on this time-like p-dualizability and the strongly time-like p-dualizability. We have the strong definition TCD and the weak TCD. So as I said, time-like p-dualizable just means that if you consider the dual problem, the Kantrovich duality holds, meaning that the maximization of the optimal transfer problem is equal to taking the infimum of the dual problem, and this can be turned into the fact that you have one optimal plan that is fully living on the time-like points, time-like related points. While if you ask for the strongly time-like p-dualizable, you are asking that all of them live on the time-like relation, meaning that there exists a common set gamma that it's contained in the time-like relation, such that every probability measure between mu and nu is optimal if and only if lives on this common set that it's inside this timelike p-dualizable, inside the timelike relations. Like asking that if you bundle together all the support of the optimal plans, they are still timelike subset. And okay, these two definitions are non-empty. If you take two probability measures with compacts sufficiently close, they are to each other, then you know that you can move one to the other following the timelike relation, and therefore they are strongly timelike p-dualizable. This was already observed by Robert in his paper in a slightly different definition. Okay, now we'll list few properties so that we can quickly move to the inequalities that I would like to discuss with you. And so if you have that is Lorentzian geodesic space that are, moreover, if you assume the non-branching condition, you have several nice properties. So this non-branching property here that I'm writing here, so this timelike non-branching means that if you have two geodesics, what you ask is that you cannot have two geodesics to coincide on a non-trivial interval and then at some point split out like two branches of a, so you don't want to have a branch-like structure. So if two timelike geodesics coincide on a non-trivial interval, then they have to be the same. In this situation, as we have already heard, so there is this theorem by Brown proving that these two, the weak TCD and the TCD coincide, and they are both equivalent to the pointwise inequality that is being proposed by Brown following the original approach of Sturm to the Riemannian CD condition. So, and you can simply ask for an inequality of the densities of the measures of the geodesic mu t going from mu naught to mu 1. So if you have two probability measures, you take that are timelike dualizable, you know that there exists an LP geodesic for which the density is written like rho t times m, and if you evaluate the density along this geodesic, then it satisfies this concavity estimate. And so this is kind of the pointwise version of the entropic definition that we have seen. So this weak TCD and the TCD, they coincide, and they can be written like a pointwise condition of the density of the Lorentzian Wasserstein geodesic. We have also seen that they are stable. So if you have a sequence of TCD EP, they will converge to a weak TCD. And there is also the analogous statement for this TCD by Matthias. And so I will now just remove this exponent E because I will always work in the non-branching situation. So all of these three notions are equivalent. And also other properties that somehow will have expanded a little bit the scope of the theory, meaning that included also interesting results with the smooth setting. Well, not so smooth setting, let's say. So Brown, yeah. Sorry, the mean free path? Mean free path. Uh-huh. Yeah. Uh-huh. Okay. Sorry, I didn't notice that. Okay. Okay. As I was saying, the distributional bounds fits with the theory of synthetic bounds. It has been proven by Brown and Callisti, and following also the work of Graf and Kunziger, Stannard-Bauer, Sojagovic, and Vigers a few years before. So they proved that if you have a Lorentzian manifold with a C11 metric and with a weight that is C1, and you consider a weighted Lorentzian manifold, so with the C11 metric, and if you would consider a weighted Lorentzian manifold, and it has weighted lower bound on the Ricci curvature in the timelike direction, the distributional sense, then it satisfies this TCD Kn condition. And so it fits with these distributional definitions, and also you can deduce some nice geometric inequalities. Here I have written down the Broom-Minkowski inequality that takes the following form. So if you have a couple of Borel sets, A0 and A1, and if you assume that they are in a timelike relation, so they are timelike dualizable. So this timelike dualizability means that we take the definition that we have seen before for the probability measures, and you ask that this property to be satisfied to the reference measure restricted to the A0 and A1 and renormalize. So you associate to A0 and A1 the two probability measures, just restricting the reference measure to them, and you ask them to be time-like dualizable. So it means that what you ask is that there exists a transport plan that is just time-like, moving mu0 to mu1. If this is the case, then you can prove these concavity properties of the measure. So the concavity of the map that at T associate the measure of AT raised to the 1 over n, where AT is just the set of convex combinations. So the union of all the T intermediate points from A0 to A1. Similarly, we also obtained an analog of the Bishop-Gromov inequality, in the sense that what we had, if you have, obviously here you cannot just take the classical Bishop-Gromov inequality, that it's just relating the volume of the bolts, because possibly here the volume of the bolts is infinite, so you have to select a sector in which you would like to test this inequality. So what we did, we considered the Bishop-Gromov only for a sector that it's called, for which we ask this condition to be tau star shaped. That just means that this set E in the future of 1 point is tau star shaped if as soon as you have 1 point inside E, know what's going on, yes, then you want all the geodesic from that point reaching X0 to be a subset of E. In that case, you have that the area of at distance R divided by distance R with R, capital R larger than small r, is bounded from below by the relation between the two radius. Okay, so now let's arrive to the new contributions that I want to present. So now the question that we tried to address was to relate in a way, so to find an analogy with the classical isoperimetric inequality that you have in the Riemannian signature. So the natural question here of the isoperimetric inequality is to relate the size of the boundary of a certain domain with the volume that it encloses. And let's say that in the Riemannian signature, so the idea is that what you know is that if you bound a certain amount of volume, that the size of your perimeter cannot be too small. No? So if you have S to be an open domain, the relation, it's the one saying that the area should be larger than a certain function of the volume of the region that you are enclosing. And so the isoperimetric problem reduces to understanding what is the optimal way for enclosing a certain amount of volume in terms of the boundary. So you want to minimize the area of the boundary and while keeping fixed the volume of the region that you have considered. And here, obviously, you have, I mean, the problem here, it's super natural. You have a bibliography that it's huge. It's impossible to mention the countless contributions. But let's say that if you want here, you have two different perspectives. One is just to understand this inequality that goes back to the classical isoperimetric inequality. So I put myself in a space and want to understand what is the best way for enclosing a certain volume, and I look for an expression, an explicit expression for this function phi. Like, for instance, the classical Euclidean isoperimetric inequality, where here the function phi is just raised into the power n minus 1 over n, where n is the dimension, and you have the optimal constant that is the one given by the unit ball. Or, for instance, on the sphere, or on the Gaussian space. And another possible point of view is the one of comparison geometry, meaning that you put yourself inside a class of spaces, verifying some, let's say, for instance, curvature information, and you want to somehow make a comparison, starting from a comparison on the geometry on the isoperimetric profile. So let's say, for instance, in the class, one of the most famous, the Levy-Gromov isoperimetric inequality, saying that if you put yourself on a Riemannian manifold with the Ricci larger than the one that you have on the sphere, then the amount of area that you need to enclose a certain volume is more than the one what you would do on the sphere. So you make a comparison between the two isoperimetric profile functions. So you say that with a lower bound, if your Ricci curvature is larger than the one that you have on your space, then the isoperimetric profile is larger than the one that you have on the space. But you can also have, for instance, a similar question imposing upper bound the curvature, on the sectional curvature, for instance, And so are two different point of views, but in the end, they somehow have many things in common. Actually, here in the Lorentzian signature, it's I think that the question is it goes in the other way around, because you have the presence of null hypersurfaces where the area can be made as small as you want. So here, the idea is that actually you have to understand the other way around. So how to maximize the area in order to enclose a given amount of volume. So you fixed a certain volume, and then you try to understand how to maximize the area in order to increase to enclose that certain amount of volume. Obviously here, because of this presence of null hypersurfaces where the metric just degenerates, you have to put some care on the choice of the competitors. You cannot simply take any domain and think about the boundary, and you have to be somehow pick the right set in which you can pose this question. Now we'll briefly list the contributions that I have found. I mean, there are not so many. If I have forgot someone, please just tell me. And so the first contribution is the one of Ban and Elrich in 1999. They put themselves in the Minkowski space, and they consider S a compact space like a coronal hypersurface containing the future of a point. And somehow they related the area of this region S with respect to the volume of the path cone of S joined to the origin of the Minkowski space. Where is chalk? Okay, sorry. So you have here S, they fix one origin, and then they just do the path cone of S through to O, and they relate the area of S with the volume of the cone here in their path. And they obtain this inequality that looks so much like the Euclidean isoperimetric inequality. And the proof goes via a Minkowski type inequality. Then in the same year, Ban obtained a two-dimensional inequality in a Lorentzian surface with Gaussian curvature bounded from above. And the picture is more or less the same. So in 2 dimensions, so this picture then reduces to being the hinge between two timelike geodesic. And here, so somehow you compare the length of a causal curve going from one end to another end of a timelike hinge. And then almost 10 years later, there's this contribution by Abedin, Corvino, Capitan, Vu, who generalized the inequality by Ban and Arich to a slightly more general framework, where instead of having here just t squared, as you would have on the Minkowski spacetime, they consider a more general weight in front of the hyperbolic metric, and they proved the same inequality for a larger class of, for a subclass of the Friedman-Robertson-Walker spacetimes, and including the assumption on the concavity of the weight, implying a lower bound on the Ricci curvature in the timelike directions. And another contribution, again, in this setting where you have almost a wedge product structure, is the one by Lambert and Scheuer 2 years ago. So here, the settings of a manifold N is obtained as the product of a real interval with a compact hypersurface S naught, satisfying the null convergence condition. And if you have S to be a space-like compact achronal and connected hypersurface, then they prove that the area is bounded from above by a function of the volume of the cone, where CS is now the region. Now here, the situation is a bit more general. So the situation here is so that you have a region S here, and you are bounding the area of S in terms of this region. That here you should think like okay, A times S naught. So and the path cone CS now is the one that you obtain from somehow matching these two S to S naught times A. And also in a different spirit, let's say that it's not just the classical isoperimetric inequality in the ambient space. After the breakthrough of Brendel that extended the classical Euclidean isoperimetric inequality on minimal surfaces, Scion 1 proved that for maximal space-like submanifold in the Minkowski space also support the same type of inequality that you have of Ban and Aleric. So these are the isoperimetric type inequalities that we have in the literature. So our idea was then to try to somehow find a way to understand if it is possible to obtain some type of result of this form in our synthetic setting. And so now we go back to our setting of measured Lorentzian geodesic spaces. And first of all, since we want to avoid, indeed, as I said, this null Hilbert surface, so the idea is just to consider Hilbert surfaces that are achronal. So we just look for achronal subset of our ambient space X. And okay, achronal just means that here it should be A. So the time-like future of A and the time-like past of A, just they have empty intersection. In this form, in this way, if your set A is achronal, what you can do, you can define the time separation function in the future and in the past of your region A, of your set A. And in this way, it's a reasonable way in this setting to define the size of the area is to make normal variations using the time separation function from your set E. So we define the future Minkowski content of a Borel achronal set by just taking the epsilon enlargement via the time separation function from your set A. So you have your region A, let's say here. And you just want to make this region here like this. Oh my God, sorry. Where is B? Yeah, A, sorry. Yeah, this is A, sorry. And so here, okay, so once that we have this way for defining the area of an achronal set, then we want also to have more or less an analogy with the idea of building a cone. So to have, let's say, a bounded region between an achronal set and something else. And this something else that we want to have, should be more or less a Cauchy Hilbert surface. And in our setting, we find a little bit more general to have the fact that this set here, so this base of the cone should be a set to be achronal plus an additional compactness. That it goes back to Galois, and it's the future time-like completeness. So a set A is future time-like complete if for each point in the future, in the time-like future, the intersection of the past, of the causal past of the point intersected with V as compact closure with respect to the ambient metric in D. And you have analogous definition for the past-time time-like completeness. And in this case, the time separation function is a little bit more regular, it's lower semi-continuous, and moreover, as soon as you have one point in the future, there is always exists a maximal, a point inside V, maximizing the distance from this point here with V. And in the case in which you are additionally assuming the global hyperbolicity. Okay, here, global hyperbolic in this setting, we can definitely say that after work by Minguzzi that this coincides with just the fact that you ask for the causal properties plus the compactness of the causal diamonds. Okay, so with these definitions that I have given, so now we have a way for measuring the area, and we have also, let's say, this analogous of the Cauchy-Hilbert surface. So we have this time-like complete subset, and the result is the following one. So if you have a global hyperbolic time-like non-branching Lorentzian geodesic space, and you ask that it satisfies the TCD 0 end condition, here I'm putting 0 for brevity, but it's the same if you have different lower bounds. And V, it's an achronal time-like complete subset, and Vt is the achronal slice at distance T from V. Then this map here, so this ratio is monotonically non-increasing as a function of time. So as soon as you take these slices and you divide by T to the n-1, this one it's not gonna increase. Let me say that similar results here are actually stronger result of this one in the setting of constant mean curvature Einstein flows, where you have pointwise monotonicity formula are due to Fisher, Moncrief, and Anderson more than 20 years ago, where they are actually considering space-like hypersurfaces that are constant mean curvature. And the parameter here is not really the time slice that you are considering from as a distance, but it's the mean curvature that it's varying. And this is has been used to study the convergence for long-time behavior of these flows. Okay, so this is the monotonicity that we have obtained, and also now let me now state the isoperimetric type property that we have devised. So now what we want to do here, we want to avoid somehow to have extra boundary component for our region S, on which we would like to bound the area. So we have actually to assume a little bit more on the boundary of S. And what we say is that S, it's an achronal subset. We say that it has empty future V boundary, so it will have no boundary with respect to the base V, if we have to ask the following condition, that as soon as you have, let's say that our region on the base here is of this form, let's say that this is V, what we would like to avoid are situations of this type here, where this one it's S. We want to say that if there exists, let's say, an integral line of the time separation function leaving from V that arrives in the future of S, then necessarily this integral line of the time separation function from V should match with S. So situations of this form where maybe you have time-like situation going like there, and then maybe you meet here are not okay, because this is indicating the presence of a boundary point of S with respect to V. So what we want to say here, maybe that this definition is not very clear, but let me just say that for sure, achronal graphs over the time slice Vt have this empty future V boundary condition. So if you have an achronal graph over the time slice Vt, then this will have empty future V boundary. So somehow what you would like to have is that if you have an integral line from the Cauchy hypersurface that is reaching the future of your achronal set S, then this means that it has to go through S. Under this condition, we have obtained the following inequality that says the following. So if you have a global hyperbolic time-like non-branching Lorentzian geodesic space satisfying the TCD0 and condition, and you have this Borel achronal time-like complete subset on which we are building our, let's say, cone. Now we take S to be an achronal with empty future V boundary in the future of V, then the following inequality holds true. So the area of S times the distance between S and V. It's bounded from above by the measure, so the volume of the cone built from V to S. So exactly this region here. So this CS is the region between S and V, swept by all the maximizing geodesic for tau V. Means for so all the integral lines leaving from V and reaching to until S. So from the dimension point of view here, we don't have the presence of the powers restoring the dimensionality, but we have that let's say a codimension 1 object here multiplied by a distance, so it fits with the full dimensional object here. That is the measure of the cone. So the flavor is that somehow the area times how much you are leaving from here to here, it's bounded from above by the total volume that you have in the cone. Okay, so now let me quickly say a few words about how to get the hands on this object. So the idea is that you would like to use, as we've seen, the information that you have on this type of spaces is the regularity in terms of the optimal transport. So all the regularity of the spaces encoded inside the Lorentzian Spacetime geodesic, and along which the entropy it's varying along it. And so the idea is to somehow include this Lorentzian Spacetime geodesics inside the geodesic leaving from V and following and maximizing the steep of the time separation function, so following the integral lines of tau V. And so the idea is that you have your region. So you have your region here, V, on which everything is happening. So now we are just focusing on the future of V because S will be a subset of our future. This will be I plus of V. And is your object S, as we've seen. So the area of S is obtained by taking smaller variations of the time separation function from S. So here we just now want to make an enlargement of S using the time separation from S. And in some sense, this should be speaking with the time separation from V, in which everything it's included. So the first thing that you do, since this object has this additional compactness property, that is this timelike completeness that we have seen before, this permits to, let's say, do a foliation of the future of V in terms of the integral lines of the time separation function. So what you do, you just foliate the future of V in terms of the integral lines of tau V. This is what it means. It means that usually tau V has the reverse triangular inequality. If you just force the triangular inequality to be an identity, this means that you are just identifying all the points just following the steepest descent of tau V. In this form here, somehow you somehow foliate with all these geodesic living with the maximal possible, maximizing at each point the distance from your set V, and by some kind of by the non-branching property of the space, this constitutes a foliation of the future of V. Let's say that in the end, what you have is that the future of V, that it's in the terminology is what is called the transport set, can be foliated by a family of these one-dimensional objects that are unparametrized timelike geodesics. So let's say here you have all of this future that is foliated by this family of one-dimensional object. And somehow now what you have, you can construct here, once that you have a foliation of the future of V, on which you can somehow see then S as a graph over here, then you can also foliate, let's say, a measure using the disintegration theorem. So each of the future of V here, M, so the reference measure here can be reconstructed by taking the summation over all this one-dimensional probability measure M alpha, living on each of these rays. And what is happening is that now, thanks to the timelike curvature dimension condition, you can really say that the reference measure M on the future can be reconstructed like just an integrating measure here that is absolutely continuous with respect to the Lebesgue measure, and just leaving there. And also, this one-dimensional metric measure space that satisfies the CDKN condition. So you have moved the geometry of the space into the geometry of this one-dimensional object. Okay, still, okay, so this curvature condition in the end arrives as saying that the density here of these probability measures are ones that are raised to the power 1 over n minus 1 to be concave, so it's just a regularity of the measure. But let's say this is just a technical. So let's say that the point is that you have the timelike complete subset. You analyze what happens in the future because it's here where we want to make variations. By using techniques from optimal transport, you could say that this foliation up to a set of measure 0 produces a decomposition of the measure and whatever. Okay, so now the point is that you want to speak between the time separation function with S with V. And what happens here is that actually you can bound from above. So the crucial part of the inequality is written in this inequality here. So this means that if you have A, so okay, here, sorry, I'm writing with S, but let's say this A. So if you have a Borel chronal timelike complete subset here, V, and if you have, you consider this decomposition on its future, both in terms of measure and as a theoretic sense, if you have a Borel chronal set in the future with empty V boundary, so it means that really you lost this component of the boundary producing bad behaviors, then its area can be bounded from above by reconstructing the one-dimensional contribution. So what you do, you just know that each set A intersects with this X alpha in one point, and it will be enough to just sum all of this one-dimensional contribution over here. And as you know here, somehow if you put yourself in the Riemannian context, this inequality would be the converse inequality, that it's indeed the one give you, I mean, using this approach, you could, for instance, prove Levi-Gromov isoperimetric inequality and other type of things, but in the Lorentzian setting, actually this inequality goes in the other way around. Because somehow what happens is that once that you are here making the, so somehow the point is that once that you make normal variations here, I mean, the time separation function of A here is more than this, and therefore you could, in principle, I mean, what you can do is that in the end, the area of your region A is bounded from above by all of these one-dimensional contributions. So somehow now here, the business is from a one-dimensional estimate to go back to and prove a full-dimensional estimate. This is another technical part that I don't want to enter too much. So here, let's say that the crucial inequality is this one, where you say that, oh, wow, sorry. The one-dimensional contributions, so this other Minkowski content on this foliation here, it's seen as a one-dimensional subset, bounds from above the area of your region here. And I don't know why, what happened? Okay. Okay, so now I think my time is over, so now let me quickly conclude. So we have also analogous result for k different than 0, but for, yeah, for better presentation, I think in the case k equals 0, it's already enough. So this one, so this inequality that I have here, so it goes in the direction saying, okay, here I'm not making any comparison with other model geometries. So a natural question here would be to say, okay, do we have a way for making a comparison between, let's say, with a Minkowski geometry and, or in the positive curvature with de Sitter and anti-de Sitter? And this is not clear so far. So let's say that the analogous of the Levy-Gromov isoperimetric inequality is still to be understood. And also a short comment on the monotonicity result in the case k equal to 0. Possibly, I mean, in the Ricci non-negative case, in the Riemann signature, in order to make a comparison between the isoperimetric behavior of your Riemann manifold with the Euclidean one, you have to impose an extra condition on the behavior of the volume at infinity, imposing what is called the asymptotic volume ratio. And the asymptotic volume ratio is well defined indeed, because from Bishop-Gromov you have the ratio between the measure of the ball and on your manifold and the measure of the ball in the Euclidean setting is monotone non-decreasing. So it makes sense to take a limit at infinity, understand what is the geometry at infinity in terms of the measure. And so possibly one could use this monotonicity in the case k equal to 0 to say that, let's say that, for instance, we have a limit that is strictly positive. This possibly could be a definition for saying that the space has Minkowski type behavior at infinity, and then from there possibly recover the a comparison in terms of the isoperimetric inequality with the Minkowski spacetime. Okay, that's all I wanted to say. Thanks.